Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.3, Problem 5. This is Section 3.3, Problem 5. It says, Dizzy Dave's Diet Supplement Clearinghouse makes two types of diet supplement pills, high-potency antioxidant vitamins and vitamins enriched with added calcium. Dave has 300 kilograms of vitamin C and 220 kilograms of calcium available each day. Each high-potency vitamin contains, among other things, 500 milligrams of vitamin C and 40 milligrams of calcium and generates a profit of 10 cents per tablet. And each calcium-enriched vitamin tablet contains 100 milligrams of vitamin C and 400 milligrams of calcium and generates a profit of 5 cents per tablet. How many of each type of tablet should Dave manufacture in order to maximize his profit? And there's a hint at the end that says pay attention to the units of measure. You want to remember that 1 kilogram equals 1 million milligrams, and that'll come in handy when we do this. So first, to set up the problem, we have 4 steps. Then to solve the problem, there's 4 other steps. So to set it up, the first step is identify the variables. The variables are the two things being made. And what's being made in this are 2 types of supplement pills. You have the high-potency one and the vitamin C one. So the high-potency antioxidant vitamin is mentioned first. So since it comes first, I'm going to make it X. X equals, and I'll just abbreviate it, hypo for high potency. And then Y is the other one, vitamins enriched, vitamins enriched with added calcium. So I'll just put calcium. So that's step 1, identify your variables. It's 2 things being made. These are the 2 things being made, the 2 types of pills. Step 2, write out your object function. Look for information that's usually about profit, usually near the end of the problem. So this one does mention profit, but it's not exactly at the end. They kind of mix the profit in with each one as they're describing it. So as I read through the problem, it mentions that each high-potency vitamin contains a few things and generates a profit of 10 cents per tablet. And then the other type of vitamin, it tells you what it contains, and generates a profit of 5 cents per tablet. So that's what we want to maximize. So we're going to maximize Z equals, so 10 cents for the first type of tablet, so it's 0.10x because I want my answer to be in dollars, plus 0.05y. So there's a profit of 10 cents per tablet for the first type of tablet and a profit of 5 cents per tablet for the second type of tablet, which we're representing with y. So that's step 2, write out your object function, which we do have. Step 3, set up the constraint. So this is the most work. So subject to. Now, what's going to limit how many vitamins Dizzy Dave can make is how much vitamin C he has. He has 300 kilograms, about 660 pounds, if you like pounds better, and 220 kilograms of calcium. So that's what's going to limit it. So let's see. 300, and I'll just put C for vitamin C. Well, the other one's calcium. Let's put VITC for vitamin C, and 220 calcium, which I'll just abbreviate CAL. Now, what I have to do is figure out how fast each tablet depletes the available resources. So each high-potency vitamin contains, among other things, 500 milligrams of vitamin C. So for the vitamin C part of it, the first tablet, each one of the first type of tablets uses up 500. And now the calcium, the first type of tablet uses up 40 milligrams of calcium. So that's 40x. The first type of tablet is X. It uses up 500 milligrams of the vitamin C and 40 milligrams of the calcium. And now the second type of tablet, it says each calcium-enriched vitamin tablet contains 100 milligrams of vitamin C and 400 milligrams of calcium. So the second type of tablet is Y. So it's going to be 100Y for the vitamin C and 400Y for the calcium. Because the second type of tablet is Y, each tablet for the second type uses up 100 milligrams of vitamin C and 400 milligrams of calcium. Each constraint has a plus between the X and Y values. Its inequality symbol is a less than or equal to. Because if you have 300 kilograms of vitamin C available, you can use up all 300, but you can't use up 302. It has to be 300 or less. Same thing with the calcium, 220 or less, because that's what you have. And the final step is, for each variable you use, you have to specifically mention that it's greater than or equal to 0. So the number of high potency tablets has to be 0 or bigger, and the number of calcium tablets has to be 0 or bigger. Now, as you set it up, this seems to make sense, and as you do the problem, if you do it like this, you're going to get it wrong. And that's why that hint is included at the end. So this follows the way we've done all the other problems, but the problem with this and why you'd get it wrong is this side of the inequality, the left side of the inequality for both my constraints is listed in milligrams. The right side of my inequality for both constraints is in kilograms. So you either have to make both sides milligrams or both sides kilograms. Then we can get it right. So I think it's easier to make both sides milligrams. Because if you make both sides milligrams, you're going to have some huge numbers. That's a hassle. If you make both sides kilograms, you're going to have tiny, tiny decimals. I think the tiny, tiny decimals are more of a hassle. So if you have 300 kilograms, and each kilogram is 1,000,000 milligrams, that means you have 300 million milligrams. Now they're in the same units. And the second one with the calcium, if you have 220 kilograms, it means you have 220 million milligrams. So now we can start actually drawing the feasible region, labeling our corner points, and sketching the answer. So we do have big numbers, that's hassle, but less of a hassle than tiny, tiny decimals. So let me start to draw the first constraint that has the 300 million. But I'm going to start it the same way as usual. Let me make my x, y chart next to the first constraint I'm going to deal with, the one with the 300 million. And I'm making my x and y's pretty wide because I know I'm going to have pretty big numbers. So first, if I put in a 0 for x, I'm going to pretend that I have an equation, not an inequality. I would have the equation 500x plus 100y equals 300 million. So if I 0 the x, I have the equation 100y equals 300 million. Well, you divide the 100 and it's going to chop off 2 of the zeros. It'd be 3 million for y. That's pretty big. Then if you 0 the y, I would have 500x equals 300 million. Well, that would be 6 million with one less zero, 600,000. Boy, I need an even wider space. Let me do it this way. 1,000 and 600. So now that was the vitamin C constraint with the 300 million. Let's do next the calcium constraint with the 220 million. So, and I want to do that in a different color because, again, it'll make the graph more clear. So I did the first constraint in red. Let me write out the second one in green. So for the 220 million constraint, again, I'm going to pretend this equals 220 million. I'm pretending I have the equation 40x plus 400y equals 220 million. Pretending it's an equation, I want to find 2 points whose x and y coordinates make that equation true. So I'm going to start by putting in a 0 for the x, I have 400y equals 220 million. So I think that's 5.5 million, but that I definitely want to use on my calculator. So 220 and then 6 zeros. I'm going to divide that by 400. It's 550,000. And then for a second point, if I zero the y, it should be the same number with an extra 0. I'd have 40x equals 220 million. I want to divide out the 40, but again, I definitely do that on my calculator to make sure. So 220 was 6 zeros after it. I'm going to divide that by 40. And it is same answer of 550,000, but one extra 0. That's what I thought I was getting before. 5,500,000. So I definitely am dealing with some big numbers here. The biggest being 3 million. Oh no, 5.5 million. Definitely don't want to run a 1 at a time number scale for this one. It would, there's not a big enough board in the world. So a million at a time would certainly be sensible. I would need 5 or 6 lines going for the x, only 3 lines for the y, million at a time. I'll actually go 500,000 at a time. So even for this, I'd need 6 lines and 11 for this. Usually I'm willing to go up to 10, one more 11. That's okay. So for 500,000, I'm going to put 0.5 m. 1 million is 1 m. 1.5 million, 1.5 m. I just don't have room to write all the zeros. Then 2 million, 2.5 million, 3 million, 3.5 million, 4 million, 4.5 million, 5 million, 5.5 million. That's enough. I have one more line. I'll do 6 million. And the same scale for the y will work. 500,000, 1 million, 1.5 million, 2 million, 2.5 million, 3 million, and that's enough. I'll put in a few more. And that way you have a reasonable scale that doesn't have millions of tiny little lines, which would be absurd. So now let's put the 2 constraints that I have with these big giant numbers onto my graph and see what our feasible region looks like. The first one with the 300 million, which was for vitamin C, I'm going to put 2 red dots and connect them because I said the vitamin C constraint in red. I go over 0, up 3 million. So on my number scale, over 0, up 3 million is a very reasonable point on my graph. Even though it's such a huge number, I go over 0, up 3 million. And then I have another point of over 600,000, up 0. I don't have 600,000 on my graph. I have 500,000, which is 500,000. So 600,000 is going to be over a tiny bit more than 500,000. So I kind of approximate by eye. So I have 2 red dots on my diagram now, on my feasible region. I'm going to connect those 2 red dots with a red line. And now I want to decide if I should shade above the line or below the line. It winds up being below. Again, my test point that I like to use is not on the line, my 0, 0, so I can use 0, 0 as a test point, my constraint. So the x-coordinate of 0 and the y-coordinate of 0 gets plugged into the inequality. 500x plus 100y is less than or equal to 300 million. When I put in 0 for x, 0 for y, I get the very true statement. 0 is less than 300 million. Definitely true, for sure. So my test point was on the underneath side of my red line. I got a true statement, so the test point is in the shaded region, which means the underneath side is the shaded side. Now, the other constraint, which I decided to do in green, which was the calcium constraint. I erased the calcium part when I adjusted my units of measure, so I'll put it back. So I'm going to put 2 green dots on the graph of my feasible region, connect them with a green line. 1 green dot is going to be over 0 up 550,000. I don't have exactly 550,000 on my number scale. So I have 500,000. 500,000 is 500,000. I want to find 550,000. So by eye, it is just very slightly higher than 500,000. And now, so there's one green dot at over 0 up 550,000. I'm going to put a second green dot where I go over 5.5 million up 0. So over 5.5 million up 0 is out along the x-axis, and I'll put a green dot on that. And I will connect my two green dots with a straight green line. And as usual, I need to decide whether I shade above the green line or below the green line. Same process. I'm going to use the test point that I like to use the most, which is 0, 0, because it's the easiest to use. So the constraint that I'm trying to graph is 40x plus 400y is less than or equal to 220 million. And now my x and y coordinates of my test point are 0 for x, 0 for y. So I plug that into the constraint for calcium, and I get 0 is less than or equal to 220 million. True for sure. So now, what that amounts to is my test point was on the underneath side of the line that I drew, gave me a true result when I tried the coordinates in my test point. So the test point's in the shaded region, which means the underneath side is shaded. And I won't even shade out in the long triangle that's formed under the green line. I'm just going to have a feasible region right near the origin, like that. And of course, the x greater than or equal to 0, y greater than or equal to 0 prevents me from using points with negative x coordinates or negative y coordinates as usual. So I have that little bit of a feasible region. It's a finite feasible region. So that's the first of 4 steps to actually find the answer, which is graph the feasible region. Now that I have it graphed, I need to label the corner points. So one corner point, if you remember this green line crossing the y-axis, crossed at a height of 550,000. So to get to this spot, I've gone over 0, up 550,000. The next corner point is 0, 0. That's easy enough. Now, the corner point of the feasible region formed by the red line coming down and crossing the x-axis is 600,000, 0. Like that. Now, there's one more corner point where the red line and green line intersect that involves big giant numbers that we have to solve. So you just have to deal with the big giant numbers. So let me trim the top of my graph a little bit where I won't be needing it, just so I have a lot of room and I won't have to squish things. And let me do it in a different color so it's not going to mix with other things. I'll do it in black. So the first constraint for the vitamin C with the 300 million, I'm going to write that as an equation, and it will be the equation 500x plus 100y equals 300 million. And the second constraint for the calcium with the 220 million will be written as an equation 40x plus 400y equals 220 million. Some big giant numbers. I could cancel the x's, which would work. The y's would probably work a little bit easier. I'm seeing the y's a little easier, less effort on my part. So I'm going to leave the bottom equation just the way it is without any change, 40x plus 400y equals 220 million. The top equation is going to get multiplied by -4. So I'm going to have negative 400y, positive 400y. When I add the equations together, the y's will cancel. I'm going to take the top equation, everything times -4. So negative 4 times 500x should be negative 2000x. And then negative 4 times 100y will be minus 400y. And then negative 4 times 300 million, it'd be 1.2 billion. Negative. So negative 1,200,000,000. That I should check on my calculator. It makes sense that that's what it is, but let's see. So I have a 12 with 8 zeros after it. And 12 with 8 zeros. Okay, so that's good, and it's negative. The bottom equation can stay the way it is. So 40x plus 400y equals positive 220 million. So now the two equations can be added together with their big, giant, enormous numbers. So for the x's, negative 2000x positive 40x is negative 1960x. Negative 400y positive 400y cancel, which is great. Now, negative 1.2 billion plus positive 220 million, I think is negative 980 million. Again, I will do that on my calculator. So the calculator says it's 9, 8, and 7 zeros. $980 million. And it's negative, because the bigger number was negative. Now, I'm really, really hoping that when I divide this negative number by negative 1,960, I get a whole number result. I think I do. So let's try it. And again, I'll do that on the calculator. So when I solve for x by dividing both sides by negative 1,960, I am very happy to see that x equals 500,000. That's a nice number. It's big, but it could be so much worse. So I have to find the y-coordinate. So what I found is the x-coordinate of the point where the red line and the green line intersect with each other. There's a y-coordinate that goes with that. To find the y-coordinate, I want to take the x that I found, go back to either of my very unpleasant original equations, and find the y that goes with it. I don't think it matters which one I pick for this. So for no special reason, I'll just pick the top one. So 500x will be 500 times the value of x is 500,000 plus 100y equals 300 million. So this I can actually do. 5 times 5 is 25, and I want to have 1, 2, 3, 4, 5, 6, 7 zeros after. 1, 2, 3, 4, 5, 6, 7 zeros. That's 250 million plus 100y equals, oops, this should have been 300 million. I was a little short on the zeros. Now, to get y by itself, I want to subtract 250 million from both sides. So I'm going to have 300 million minus 250 million, which I can actually do without my calculator, is positive 50 million. Now, to solve for y, I'm going to divide by 100, which is basically going to wipe out 2 of the zeros. So I'd have a 5 with 1, 2, 3, 4, 5 zeros. So y is a 5 with 1, 2, 3, 4, 5 zeros, 500,000. So the x is 500,000, the y is 500,000, and by my graph, that seems pretty close to right. So we did manage to graph the feasible region. and label the corner points. Now what I have to do is fill in that chart. So I have a lot of room right there. Let me fill in the chart. And again, I'll do a different color just to be clear what step I'm on. So this is the third of 4 steps. And I should make this chart fairly big because I'm going to be putting in some fairly big numbers. So one column is for corner points. The middle column is for the object function, which for this particular problem is 0.10x plus 0.05y. And the last column is for output. Now I have a feasible region that involves 4 corner points, one of which is 0, 0, so that's easy. But I'm going to need 4 rows. So now, list the corner points. One corner point is 0 for x and 550,000 for y. The next corner point is 500,000 x, 500,000 y. The next corner point is 600,000 x and 0 for y. And the last corner point is 0 for x, 0 for y. And again, this represents the number of the first type of pill and second type of pill that can be made with resources available. So for the first corner point, which means making none of the first type of vitamin, the high potency, and only the second type, the calcium, for as many as you can do until you run out, how much profit would you make? So my object function, 0.10 times x, becomes 0.10 times 0, plus 0.05 times 550,000. Well, the 0.10 times 0 is easy enough. That's 0. 0.05 times 550,000. Well, if it was 0.10, it would be 55,000, it'd be half of that. So it should be 27,500. Better check it. 0.05 times 5 with 4 zeros. 27,500. So now we add 0 plus 27,500. That I can do without my calculator, is 27,500. So you make a profit of $27,500 by making no vitamin C or high potency vitamins and 550,000 calcium. So now the next one, 500,000 of each type of pill. So going back to my object function, 0.10 times x becomes 0.10 times 500,000. And 0.05y becomes 0.05 times 500,000. So 0.10 times 500,000 should be 50,000. It is 50,000. 0.05 times 500,000 is going to be half as much. It's going to be 25,000. So 50,000 plus 25,000 is 75,000. Well, that's quite a bit more. So you can make $75,000 of profit by making 500,000 of each type of pill. And the next corner point, 600,000, 0. So 0.10 times x becomes 0.10 times 600,000. And 0.05y becomes 0.05 times 0. 0.10 times 600,000, the 0.10 chops off of 0, it's going to be 60,000. The 0.05 times 0 is just 0. So 60,000 plus 0 more is 60,000. So you can make a profit of $60,000 by making 600,000 of the high potency vitamins and 0 of the calcium vitamins. And the last corner point, 0, 0 is going to give me a 0. So 0.10 times x is 0. 0.05 times y is 0.05 times 0. So you'll have 0 plus 0. You have a profit of $0 by not making any pills at all. So we want to find the maximum profit. And our choices for available amounts of profit are $27,500, $75,000, $60,000, or $0. Well, clearly the $75,000 is the most profit you can make for what you have available. So let me write, I can fit it right underneath here, and green is probably a good color. So maximum profit of $75,000 by making $500,000 high potency tablets. That's the first type of tablet. And $500,000 vitamin C tablets, the second type. So a maximum of $75,000 of profit by making essentially $500,000 of each type of tablet.